In this lesson, we will discuss the construction of aircraft's fuselage, wings, and tailplane. There are three main types of fuselage construction in use. First, there is the truss or framework type, which is generally used for light, non-pressurized aircraft. Then there is monocoque, which is only rarely used. And finally, semi-monocoque, which is in use on most other types of aircraft. The last two types of structure are more generally referred to as stressed skin. The framework or truss consists of light gauge steel tubes welded together to form a space frame of triangular shape to give the most rigid of geometric forms. Each tube carries a specific load, the magnitude of which depends on whether the aircraft is airborne or on the ground. It is a strong, easily constructed, and relatively trouble-free basic structure. The framework is covered by a lightweight aluminium alloy or fabric skin to give an enclosed, aerodynamically efficient load-carrying compartment. Monocoque is a French word meaning a single shell. In a monocoque structure, all the loads are taken by the stressed skin, with just light internal frames or formers to give the required shape. Sandwich construction, which is a honeycomb core with a skin of aluminium alloy or composite material such as glass reinforced plastic or carbon fiber reinforced plastic, can be used to provide rigidity and strength. However, even slight damage to the skin can seriously weaken the structure. To be a true monocoque, the structure would have no apertures in it at all. But for practical purposes, they have to be provided for access and maintenance. The apertures need to be reinforced so that the integrity of the structure is maintained. Once the aircraft doors are closed and all the hatches and access panels are fitted, the fuselage is, to all intents and purposes, a monocoque structure. One of the few examples of monocoque fuselage constructions is the Beech Starship. As aircraft became larger and the air loads greater, the pure monocoque structure was found not to be strong enough. Additional structural members, known as stringers or stiffeners, and longerons are added to run lengthwise along the fuselage, joining the frames together. The light alloy skin is then attached to the frames and stringers by riveting or adhesive bonding. Stringers stiffen the skin and assist the sheet materials to carry loads along their length. On pressurized aircraft, they take some of the strain caused by the pressurization and convert it into tensile stress. Longerons are more substantial than stringers and are fitted where extra strength is needed, such as for the seat rails in passenger aircraft. When cutouts are made to stress skin structures, for example to provide access panels, doors or windows, or when repairs are required to damaged areas, reinforcement in the form of doublers or backing plates is required around the cutout. If the skin is machined from solid metal, then that part around the cutouts is left thicker than the rest to provide the required reinforcement. The flight deck windows fitted to pressurized aircraft must withstand both the loads of pressurization and, because birds also use the sky and are not under air traffic control, they must bear the impact loads from possible bird strikes. To do this, they are constructed from toughened glass panels, attached to each side of a clear vinyl interlayer. Windscreens are surrounded with a rubber seal and attached to the frame by bolts passing through the extended edge of the vinyl interlayer. An electrically conductive coating applied to the inside of the outer glass panel is used to heat the window. This prevents ice from forming and maintains the window's flexibility, making it more able to withstand bird strikes. The shock loading of a bird strike impact is absorbed by the ability of the vinyl interlayer to stretch and deform should the impact be sufficient to shatter the outer glass. The aircraft must be capable of continued safe flight and landing after impact with a 4-pound or 2-kilogram bird when the velocity of the aircraft is equal to its design cruise speed, VC, at sea level, or 0.85 VC at 8,000 feet, whichever is the most critical. In other words, the windscreen must be able to withstand this impact without penetration.